Since you are not going to spend your time memorizing the periodic table, you'll need to have a copy of the class table available in order to determine the molar mass. There are definitely some elements you'll end up memorizing by accident, but it shouldn't be a goal of yours to know every value on this table. To determine the molar mass, we need to determine an atom count and then locate molar masses on the periodic table. I'm going to approach these examples fairly systematically and with a table so that all of the pieces are as clear as I can make them. But know that I don't write these things out in a table when I calculate molar masses. I've had enough practice that I can do the atom count and keep track of parentheses in my head or my calculator. If you get to that point as well, then cool. If not, try this table approach. As I mentioned, I'm going to do this as systematically as I can for clarity using a table. To fill in my table, I'll need to identify what elements are present in my compound, how many of that element are present, what the molar mass of that element is, and what the total contribution from that element is if there are more than one of that atom present. For our first example, which is sodium chloride, there's a single sodium ion and a single chloride ion. I will need the molar mass of each atom, which I can locate on their periodic table entry. Since there is a single ion of each, the total contribution of each element is simply equal to the element's molar mass. My last job is to simply add these contributions together to determine the molar mass of the compound. Note that if I'm talking about molar mass, which I have been here, the result of this calculation will have units of grams per mole. If I'm talking about an individual formula unit or molecule, then the result of this calculation will have the units of AMU. Whichever unit you have, you'll end up with the same numerical value. We have larger subscripts here, but our process is the same. You'll have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms in your compound. Next, you'll locate the molar masses that you need from the periodic table. Since we have subscripts that are greater than 1, each of our atoms will have a contribution to the overall molar mass that is not equal to the values pulled from the periodic table. To figure out the contribution, simply multiply the number of atoms present by the molar mass of an atom. For carbon, that would be 6 times 12.01. For hydrogen, that would be 12 times 1.01. And for oxygen, that would be 6 times 16. At this point, you simply sum all of the contributions to determine the molar mass of your molecule. First, figure out your atom count. We have 3 sodium, 1 phosphorus, and 4 oxygen in our formula unit. Next, find their molar masses on the periodic table. Since there are more than 1 sodium and oxygen, you'll also need to find their contribution to the total molar mass. Lastly, sum up all of the contributions to determine the molar mass of the formula unit. Parentheses often trick some students because they forget that an exponent on the outside of a set of parentheses means that there are multiple of that entire grouping. In this case, we have 2 phosphate anions. If each phosphate contains 2 phosphorus and 4 oxygen, then 2 of those groupings would contain 2 phosphorus and 2 oxygens. We have 3 calcium ions to balance the charge. Locate the molar mass on the periodic table. This looks a lot like the last example, just with calcium swapped for our sodium. Here, none of our atoms are present in a singular quantity, so you will need to multiply the number of atoms present by the molar mass in all 3 cases. Once you have done all of that, you simply sum the column to determine the molar mass of the compound. This is an example of a hydrate, or a crystalline compound that has water molecules trapped in the crystal structure. Since those water molecules are there until you remove them by physical means, usually heating, they would be associated with the compound if that compound were placed on a balance, which means any calculations performed using the molar mass of these compounds would also have to take those waters into account. This isn't a big, huge deal though. It really just gives us a handful more atoms to account for in our atom count. Our process for magnesium and sulfur is unchanged. There are 1 of each, so we will include one of each in our chart. The oxygen count is probably the hardest to figure out, though it's not too hard. There are 4 oxygen atoms associated with the sulfate, but there is also an oxygen atom in each water molecule, and there are a total of 7 water molecules. The 4 from the sulfate and the 7 from the waters give us a total of 11 oxygen atoms. Our hydrogen atoms will all come from the waters. If there are 2 hydrogens in each water, and there are 7 total molecules of water, there's going to be 14 hydrogens in this compound. The atom count is the only thing that gets special consideration when dealing with a hydrate. So you would still just grab molar masses for the atoms off the periodic table, then figure out the contribution of each of the atoms, and then sum up all of those contributions.